Good morning, everyone. My name is Anthony Percival, and today I'll be discussing the paper Growth, Water Use Efficiency, Stomatal Conductance, and Nitrogen Uptake of two lettuce cultivars grown under different percentages of blue and red light. This paper is by Clavijo-Herrera, Santen, and Gómez. I picked this paper because my thesis research has a lot to do with studying plant responses to light quality. That is, like how much red, green, blue light you apply to plants, the timing of that application, the ratio of those different components. Um, but I don't look a lot into water relations, or I haven't thus far. And I think this paper does a good job of bridging the gap between my research and what we talked about in class so far. With that, I want to start with a little introduction to LEDs. So LEDs are light fixtures that are becoming more and more common in both the plant production setting and plant research. This is because LEDs are incredibly energy efficient and they don't produce a lot of heat, meaning you can put your fixtures closer to your plants without worrying about frying them. You also can customize the spectrum output, meaning you can control how much red, green, and blue you're applying to your plants, which has uses in research. It provides a lot of flexibility in determining plant responses to various wavelengths, not just how much red, green, and blue, but specific wavelength of green, red, and blue differences. Um, and this has an impact on production because one of the goals in horticultural research using LEDs is to try and develop general lighting recipes for horticultural crops so that growers are able to achieve the highest quality production. Building on that a little bit, I want to talk a little bit about red and blue light because the authors of this study are concerned with how increasing percentages of blue light affects plant responses. So we all know that chlorophyll absorbs mainly in the red and the blue. The blue light being from 400 to 500 nanometers approximately, and the red light being about from 600 to 700 nanometers. But these light qualities are not equal in how they drive plant responses. Two important examples that are cited by researchers are that blue light, when compared to red light, has a lower quantum efficiency in driving photosynthesis. That means if you have an equal number of photons, applying the blue light is going to result in reduced photosynthetic products compared to the same amount of photons applied as red light. And the opposite trend is kind of seen in driving stomatal aperture, where blue light has a higher quantum efficiency than red light in driving stomatal aperture, meaning that it's more efficient in opening stomata for the same amount of photons. Some other important plant responses to blue and red light. Blue light has shown to reduce leaf area and leaf number. It's also shown to correlate to high stomatal conductance and an increased stomatal index. This stomatal index is basically how many stomata you have per epidermal cell. And then red light, when applied as monochromatic red, meaning only red light, has shown to promote shade avoidance responses, as well as stomata that don't respond readily to changes in light quality. So, the author's objective was to examine the growth, water use efficiency, stomatal conductance, SPAD index, and shoot nitrogen uptake for two lettuce cultivars under increasing percentages of blue light in a sole source lighting environment, where sole source lighting environment is one where the only light that plants receive is the light that we provide, through LED fixtures or some other kind of light fixture. They hypothesized that as the percentage of blue light increases in a treatment, plants will be more compact, have a higher SPAD index, that is, higher relative chlorophyll content, and have increased rates of stomatal conductance, water and nutrient uptake, and have lower water use efficiency, where in this study, water use efficiency is basically the amount of biomass produced relative to the amount of water used by a plant. So they used two cultivars of lettuce. They used Cherokee and Waldman's green, a red leaf and a green leaf lettuce. To germinate the plants, they put seedlings of both cultivars into a growth chamber under broad spectrum LEDs. That is, the LED's output included kind of a full spectrum that included red, green, and blue light at a photosynthetic photon flux density of 180 micromoles of photons per meter squared per second. After 2 weeks in these conditions, the plants were transplanted to individual containers and placed into the respective lighting treatments. So there were 5 plants per cultivar per lighting treatment per replication, and they had 3 reps. The container surfaces were covered with plastic film that still allowed the plant to poke through, of course, to minimize water lost from the substrate, because you don't want to include that in water use by the plant. Excess shoots of each cultivar were ground for nutrient analysis at week 0. Plants were rotated within lighting treatments in order to minimize location effects, which is common in controlled environments because you might have slightly different incident radiation at different points in your treatments. So you want to rotate your plants. And then the plants are watered every 3 days using an irrigation reservoir, and the water that drains out of the bottom of the pot is returned to the irrigation reservoir because when calculating water use, you also don't want to include water lost as drainage. So they had 7 lighting treatments, everything from 100% red light to 100% blue light, referred to as monochromatic red and blue. But they also had a broad spectrum treatment and then different ratios of red to blue light. Each treatment, regardless of light quality, received 17.5 moles of photons per meter squared per day with an instantaneous photosynthetic photon flux density. So how many photons per second was 270 micromoles per meter squared per second with an 18-hour photo period. So the 18-hour photo period is basically how long the LEDs remained on. This figure 1 is really useful in really looking at the differences between the treatments. I'm not going to go through each one, but I recommend you pause it and kind of take a peek. But a way to look at it is you have your wavelengths of light down here on the bottom, and you can see that in the 0% blue treatment, you have a large spike between 600 and 700 nanometers. This represents the 100% red, 0% blue treatment. But then as you increase in your percentages of blue light, you can see that you have that spike in the blue until you no longer have anything in the 600 and 700 nanometer range, indicating this is the 100% blue treatment. So they also controlled carbon dioxide, relative humidity, and temperature to reduce those confounding variables, to reduce that residual variation. The experiment was concluded 21 days after plants were placed in the treatments. In order to calculate water use, they weighed the irrigation reservoirs using a digital balance prior to refilling the irrigation reservoir with new solution. Excuse me. 5 samples of moist and dry substrate were weighed at the beginning and end of the experiment to determine water in the substrate, because you also don't want to include that as water used by the plant. This was subtracted from total water use. They measured stomatal conductance 19 days after the plants were placed in the treatments using a pyrometer, and the SPAD index was calculated by taking chlorophyll measurements, 3 measurements per plant at different points on the youngest fully expanded leaf prior to destructive harvest, and your leaf number leaves were counted at the 21-day mark. Total leaf area was measured using ImageJ, which is a computer program. Dry mass was calculated by drying the shoots at 70 degrees and then weighing them. They didn't do any work with the roots in this experiment, unfortunately. Specific leaf area was calculated by dividing leaf area by dry mass. Tissue nitrogen content was measured using semi-automated colorimetry. Nitrogen uptake was calculated by multiplying the initial shoot dry mass by the initial tissue nitrogen content and then subtracting that from the final shoot dry mass multiplied by the final tissue nitrogen content. And then water use efficiency was calculated by dividing the total shoot dry mass by the total amount of water used per plant. So what did they find? So aside from the 0% blue treatment, both parameters, leaf area and specific leaf area, increased with increasing blue light up to 66% blue. So you can see that in figure 1 in sections A and B. You have your leaf area and it increases to about 66% blue and then levels off. Your specific leaf area shows a similar trend. I do want to make note that specifically in their regression analysis, they did not include the 0% blue treatment because it was just vastly different than all of the other treatments. This has been done in horticultural studies in the past. And they also didn't include the broad spectrum treatment because they were concerned about the interaction between green and blue light, as green light is generally thought to counteract the effects of blue light in non-photosynthetic processes. So, leaf number. So the regression analysis showed that for each 10% increase in blue light, plants produce one less leaf, and there were 4 to 6 times as many leaves in the 7% and 26% blue treatments than in the 66% blue treatment. And then there were no significant differences in leaf number in treatments with 52% blue or less. So you can kind of see that, this is still figure 1, section C. You can see that as blue light increases, down here on the bottom, your leaf number has a generally decreasing trend. And they also found that dry mass decreased with increasing blue light. Plants under 7% blue light had significantly higher dry mass than plants under the 66 or 100% blue treatments. And you can see that trend here. There's a general decrease in dry mass as you increase blue light, although it kind of levels off here at your 66% and 100% blue treatment. In terms of the physiological results, water use efficiency decreased with increasing blue light. It was significantly higher under the 100% red, so that's the 0 blue treatment, and the broad spectrum treatment compared to the 66% and 100% blue treatments. So you can see water use efficiency as blue light increases, water use efficiency decreases. And here you can see that red treatment and that broad spectrum treatment represented by the triangles. For stomatal conductance, your stomatal conductance generally increased by 10 millimoles per meter squared per second for every 10% increase in blue light. So your stomatal conductance was 87% higher under your 100% blue treatment compared to the 0% blue or broad spectrum treatment. And your stomatal conductance was 48% higher under your 66% blue treatment compared to your 0% blue treatment, that's the 100% red treatment, and the broad spectrum treatment. And you can see the stomatal conductance. This is figure 3, section B. So as blue light increases down here on the bottom, you can see that stomatal conductance increases, with stomatal conductance being noticeably lower in your 100% red and broad spectrum treatments. In terms of your SPAD index, your chlorophyll content increased as the percent of blue light increased, except under 100% blue light where there was a slight decrease. And your chlorophyll content was significantly higher under 66% blue than under 0%, 7%, or the broad spectrum. So you can see that your SPAD index generally increased as you increase the percentage of blue light until you get to that 66%, until it starts to decrease again. You can see that that 100% red treatment, that 0% blue, has significantly lower chlorophyll than your other treatments. And there was no significant difference in nitrogen uptake. Okay, so expanding a little bit on these results. So the trends in leaf area, in specific leaf area, didn't match other literature looking at lettuce responses to light quality. Generally, your leaf area decreases under increasing blue light, but that was not the case in this study. Despite that, as blue light increased, your dry mass still decreased, but the authors hypothesized that this was because your reduced leaf number also results in decreased light interception, where they originally hypothesized that decreased leaf area would be the main driver behind that. In terms of chlorophyll content measured by the SPAD index, your SPAD index increased with increasing percentages of blue light. This is thought to be because blue light has been shown to upregulate the biosynthesis of chlorophyll, while red light has been shown to downregulate it. There's some more details in some gene interactions in the paper that I don't think I am qualified to really speak on more than that. But it's kind of cool to think about it as potentially part of a shade avoidance strategy to maximize light interception in light limiting conditions. Because if you think about getting lower light levels or having fewer leaves, you want to maximize the amount of chlorophyll in each one of those leaves. So any light you do intercept is converted to photosynthetic product as efficiently as possible. So, in terms of stomatal conductance and water use efficiency, we saw higher stomatal conductance and lower water use efficiency in treatments with higher percentages of blue light. And the authors proposed two hypotheses to explain this. The first was that blue light has a lower quantum efficiency in driving photosynthesis, but a higher quantum efficiency in driving stomatal aperture. This basically means you get less photosynthetic product per quantity of water. This is supported by some other studies that have shown that under blue light, leaf conductance also increases. This is also supported by a greater stomatal index being found in horticultural crops under blue light. Not just lettuce, there was also, I think, cucumber and tomato. This was found in those leaves. The second hypothesis, which I think is incredibly interesting, is the increased stomatal conductance and decreased water use efficiency is a strategy of evaporative cooling in response to high blue light. And the idea behind this, which is proposed by Runkle, who's, I think, at Michigan State, is that roughly 20% of blue photons are absorbed by non-photosynthetic pigments like anthocyanins, and this could lead to that energy warming the leaves without an exchange of fixing carbon, because the leaves are unable to use all of the absorbed blue photons. So the plant is pretty much heating up and thus needs to increase stomatal conductance and decrease water use efficiency by opening those stomates and increasing evaporative cooling. And previous studies have shown that higher rates of evaporative cooling with greater stomatal aperture and greater stomatal conductance. So they're better at cooling themselves off by opening up those stomata and letting more water flow through. So in conclusion, with all other conditions controlled, spectral quality was shown to significantly affect water use efficiency in controlled environments. Broad spectrum LEDs generally have higher water use efficiency compared to red-blue LEDs with greater than 60% or 66% blue light. And to increase water use efficiency, it may be necessary to add some supplemental green light, as I may have mentioned earlier that green light has been shown to counteract the effects of blue light in terms of stomatal opening and a few other photophysiological processes. That's all I've got for you all today. I hope you enjoyed reading the paper, and I hope you enjoyed this presentation. I think I went a little bit long. I think I'm probably around 18 minutes. I'm not sure how we're going to do like a question and answer thing for these discussions, but feel free to email me, or we may, I think Yeling mentioned setting up a Skype discussion or something like that. So whatever the choice may be, I'm happy to discuss this paper with you further, or if you ever want to talk about light, just like let me know, because it's kind of my thing. But yeah, I hope you all enjoyed the paper and the presentation and are doing well in self-isolation.